Honors Algebra 2, Chapter 4 and 5, Section B, or Part B, Section 5.2. So we talked about graphing polynomials the past two sections in the different forms. We're now going to talk about graphing all polynomials. Quadratics are a part of polynomials, but they're one kind of function. There are other functions within this family of functions. So we need to know the parent functions we're going to talk about here, how to sketch them, and then be able to know these different behaviors of the parent functions. So if we were to sketch this, we should know right away that y equals x squared is a parabola that has 0, 0 as a point. That's actually the vertex. If I plug 1 in, I'm going to have 1 as a y, 2 is going to be 4. And so we can quickly plot points here to help us sketch the parabola. Now, if we were graphing y equals x cubed, still making a table, now if I plug in points, similar points we had, 0 is still 0, 1 is 1, 2 is 8, it still grows. When I plug in a negative value here, it actually stays negative, because a negative 1 times a negative 1 times a negative 1 is still negative. We get a negative 1. If I plug in a negative 2, we actually get negative 8. So where a parabola, they turn back to become positive. So like 0, negative 1 becomes 1, and negative 2 would become 4 for this. For this cubic function, they actually will become back to negative, or go negative. So if I plot these points, 1, negative 1, 2, negative 8, 0, 0, 1, 1, and 2, 8. We have this shape, which there's a few names that teachers have for it. People will call it like an S-type shape. I've heard disco shape. But this is the cubic shape, the cubic function is what that would be. So we have different functions within the polynomials, and they go by the powers. So here is x squared, here is x cubed. So the family of function, you should have an idea of what the shape looks like. So looking at the parent functions, if we have x squared, x cubed, x to the fourth, and x to the fifth as the polynomials we're going to look at. And then we also are going to look at our a value. Our a value can be positive, our a value can be negative. These all have a values, and for the two up here, we've seen our a value here. Our a value is positive 1 and positive 1. So when we actually sketch it, x squared, the positive a value is a parabola that opens up. Negative a value just opens down. Cubic will have this cubic shape, like disco, or John Travolta we say, or the S shape is positive. Negative would be going downward, so this is a negative a, so as I go left to right on the graph, we're actually going downward on the graph. X to the fourth would be the W, and then it could be downward. Now, it doesn't have to have this extra hump in it. It could be just a regular parabola as well, but the most extra humps in this, extra turns in the graph it could have, is a W shape or an M shape. X to the fifth. Notice how for the odds, the arrows go in opposite directions. So for the arrows, it could be like this. And so we could have more humps in this as well. We could have the extra hump in it. So think of Fergie, the bigger the degree, the more humps, the more humps. And so here we have the x cubed. X cubed could actually have a little hump in it as well. And so these are different shapes. So you should have an understanding when I see x to the fourth as the degree of it, what the shape could be just by the degree of the polynomial. And then knowing if it's increasing or decreasing by the sign of a. So right away when we see this, y equals 2x cubed, you should have a picture in your head. I know it could have this shape, and I know it could have this shape. One of those two. It's increasing because our a value is positive. So we have a positive 2 is our a value, so I know what the shape is. So when I plot that 0, 0, 0, 0 I know here is the inflection point. And let me actually go back and show you what the inflection point is. The inflection point in this graph is similar to like the vertex in this graph, where the graph, as you move along it, if you look at the rate of change in these points, it's decreasing, it's becoming more flat. And then after that point of inflection, it becomes steeper again. And that's kind of how it moves along the graph. That's called the point of inflection. The point of inflection is like the vertex. It has similar meaning when you find the values of it. So here we have the point of inflection. If I go right one, I'm going to go up the power of a, or the awesome a, the 2 value. That's the awesome a value. If I go left one, I'm going to go down 2. Now if I plug in 2, I can do 2 cubed, 8. 8 times 2 would be 16, so it increases rapidly here. So you can kind of see that shape. But awesome a value helps us find those points quickly. Here, x to the 4th, it could have the m or the w, but because we have a negative a value here, I know it's got to go downwards. And it could be an m, it could just be a parabola going downwards. And so if you plot points, we still have the vertex at 0, 0 here. If I plug in 0 for x, I get 0 for y. If I go one right, I'm actually going to go down at half. Here's the general shape of that. Same thing here. If I go right 2, I plug in 2. 2 to the 4th is 16. Negative half times 16 is negative 8. Down here at negative 8. So you can see the shape of the graph. And again, it's increasing quickly, or decreasing quickly. So we can graph by just making a table when we're graphing these, but we also have something called end behavior, and that just means as we go forever to the right, what's the shape of the graph? What's the y values doing? As we go forever right, the graph here would be going up. As we go forever left, what's happening to the graph? We're going to go down. So it's kind of looking at the arrows of the graph. As we go forever right, we're going to go up. As we go forever left, the graph is going down. So the notation down here says as x goes to the right, as x goes to positive infinity. The symbol means positive infinity means to the right forever. The y values would go up. So the y values go to positive infinity. As x goes left forever, the y values go down forever, so negative infinity. And so this would be the same kind of deal here. As we go forever right, the graph goes up forever. As we go forever left, the graph still goes up forever. So these are both positive infinity and positive infinity. So for these two graphs, you're looking at these arrows, the end behavior, not around here, not in the middle, but forever right, forever left. So even if I had an extra hump in the middle here, I'm really looking at the end behavior, or what's happening at the end of it. Vertex form. So similar to quadratics, we had vertex form. For all polynomials, we have that, and we can use the same knowledge of vertex form for parabolas and apply them to this. So HK is the vertex or the point of inflection, so you can find those quickly. So for this graph here, we can find the vertex first. So our vertex here is -1, -4. So you can find that vertex first, -1, -4. Then we want to plot some more points. Now our a value is the number that's being multiplied to the parenthesis. The number outside of that parenthesis is going to be distributed through there. So our a value is 1, so if I go right 1, I'm going to go up 1, the awesome a value, left 1, up 1. I know they're both going up because it's a even exponent. So I know the end behavior would be a kind of like a parabola. It could have some humps in it, but the end behavior would be a parabola. If I plug in 1, and so you just plug in 1 in for x and evaluate, 1 plus 1 is 2, 2 to the 4th is 16, 16 minus 4 would be 12. So I'm actually going to be off the graph a little bit. That's how fast it's increasing. And I can try sketching a graph here. Oh, that was horrible. Then we can sketch a graph here. So it increases so fast, my tablet's drawing straight lines. So here we have a similar problem here. Our a value is 1. Our point of inflection here is going to be 2, -8. So 2, -8 down here. So our point of inflection. Then our awesome a value, we go right 1, we're going to go up 1. Now we need to be careful here. We need to look at our degree. Our degree is the third power. So I know the shape is like this. So I know we go opposite directions. So if I go right 1, I go up 1. Go the other direction, I'm going to go down 1 to hold that shape, or to keep that shape of the graph. Now I might plug in 4 to see, because 4 might end up on the graph. 4 minus 2 is 2, 2 cubed is 8, 8 minus 8 would be 0, to help me graph it. So there's the sketch of that graph. For this one, it's a little more added to it. Our inflection point is 5, 4. And our A value here is right 1, down 2. Cubic, and our A value is negative. So I know it's going to be going downward in the cubic shape. So we have a right 1, down 2. If I go left 1, go up 2, then that would be the shape of the curve. So there's a graph. You can find the end behavior for these graphs. I look at the end behavior of my arrows. They're both going up for this. So the parabola shape should be pretty easy. Both going up, both going to be positive. Here they're going opposite directions. As we go right, it's going up, so that's positive. As we go left, it's going down, so it's negative. So the graph goes left, the arrow's going down. And for this one, it's actually opposite. As we go right, the graph are going down more, so it's going to be negative infinity. As we go left, the graph is going up, so it'll be positive. Those are end behaviors. So graphs of polynomials. We'll do some more of this in class tomorrow, but we're going to introduce it today. So given these functions, this equation right here, which is not in that vertex form, it's in standard form, it's a little harder to graph, and plotting points will take a while. So we'll use our calculators to help us out. And so we take this and actually plug it in your calculator. So like y equals, plug in this equation, and you graph it, you should get this graph. That's the graph you should get. So then if we look at this graph, we have these point of inflection here. But we also have these points, which are called maximum values and minimum values. This is called a relative maximum. This one here is called a relative minimum. And the reason why is if you look in the small window, the window right around here, that point is a maximum. And down here in this window, this point would be a minimum. So these are called relative maximums and minimums. We're kind of ignoring the end behavior and looking at a small window. So we'll go over how to find maximums and minimums. We'll let our calculators find those on how to find max and mins. The degree of this, we should be able to pull from the equation. The degree of that is a 3. The leading coefficient is the number in front, which is 1. And then our end behavior, as x goes right, f of x goes up. As x goes left, the graph goes down. So we can pull out that stuff. The max and min we'll talk about tomorrow. And so we have another graph here. So you plug this in your calculator, and you have multiple terms, multiple max and mins. But we have a degree, leading coefficient, and then end behavior. So I want you to try finding the degree, leading coefficient, and end behavior for this graph. And I'll help by putting little arrows in to help you out a little bit. But tomorrow, turn your paper in with the degree and the leading coefficient, and then the end behavior for this graph. I think I'm going to call it good right there, so have a good night.